Very, very quickly. You can, in principle, realize this type of physics in these 2D sodium iridium oxide and lithium, the alpha lithium iridium oxide. Okay, I won't do that again. So we know that they're not spin liquids, right? We know they order magnetically into the zigzag pattern for the sodium, and for the alpha lithium, some indications of spiral order. Again, there's no definite statement on that just yet. So what else do we know about this order? Well, you might think that if we see this thing order, we might have gotten spin liquid physics completely wrong. Maybe it's not KDEV, maybe it's something Heisenberg-like. Recent evidence shows that it's not true, that the spatial and spin correlations are in fact tied together. You can see here this lovely data that the wave vector and the spin correlations are strongly correlated in this material just above the transition. So you should still expect strongly anisotropic interactions even if we moved away from the KDEV limit. I should have left it there. No, it turned itself off. Sorry. It's got to reboot. So I should have moved it. Okay, that's where we were. What else do we know about the zigzag phase? Sorry for the technical delay. So one important feature that hasn't been pointed out so much in the talk so far today is this inelastic neutron data on powder samples, where you see that in the ordered phase below this transition at 15 Kelvin, there's some amount of scattering that's at quite low energies. So from probes like RICS, you expect the energy scales in these compounds to be quite large, on the order of tens of MeV. Here we're seeing scattering down to essentially their resolution, 1 or 2 MeV. So that's sort of one piece of information, one of the only pieces of information we have about the low energy structure of this state beyond the ordering vector. So the sort of canonical theoretical approach that's used is to study this Heisenberg-KDEV model. You've seen much of today, this bond-dependent KDEV exchange plus this isotropic Heisenberg. Physically, as I noted, you could get this from an oxygen-mediated path where you go into the oxygen to get between the d orbitals. This J can be generated from some direct exchange between the d orbitals. And the phase diagram of this model has been studied extensively, as again, you've already seen today. Quickly. So there's sort of 5 phases. There's this KDEV spin liquid, which survives finite Heisenberg coupling. There's a large anti-ferromagnetic phase and a large ferromagnetic phase near the anti-ferromagnetic Heisenberg and ferromagnetic Heisenberg limits. And as well, there's the stripy phase and the zigzag phase that appear when these that appear next to the KIDAV phase when you add finite J. So you see that there is a zigzag phase in that phase diagram, at least somewhere. Do the properties of that phase, ignoring how we got to that point in the phase diagram, agree with the properties of the material? So you could look at this excitation spectrum to try to figure this out. So if you do a sort of semi-classical calculation, 1 over S type treatment of the excitation, you find that there is low energy excitation even in this highly anisotropic model. This is essentially due to some accidental classical degeneracy in Heisenberg-KIDAV model. But you're still stuck with this fact that this KIDAV coupling needs to be on the positive side, near the anti-ferromagnetic KIDAV limit. So from this oxygen-mediated type argument, you expect this coupling to go negative. And ab initio studies have sort of been very consistent with that recently. So what's going on here? So there have been some proposed solutions to this, many by at least 5 people in the audience, where you can, for example, flip the sign of K by adding additional exchange paths, add various types of further neighbor couplings, either Heisenberg or, as we heard earlier from Talia, second neighbor KIDAV. You can include monoclinic distortions, or you can actually include all of them all at once. I might have missed some, but there's at least a handful of proposals that can solve this problem. So let's sort of look at this in general and say, what's the sort of couplings that are allowed in this material? So realistically, this structure has both monoclinic and trigonal distortion, and you might expect second and even third neighbor couplings to be important. So if you just look at each bond, for example, the nearest neighbor bond, there are 4 symmetry-allowed exchanges. And because of monoclinic distortion, this bond is slightly different than this bond. And so there's actually another 6 exchanges allowed on that bond. So at nearest neighbor, we're already at 10 symmetry-allowed exchanges. Now we start doing second and third, even ignoring the monoclinic distortion, we had at least another 8. So, there are people, some in the audience, who are brave enough to study this full model with all 20 or so symmetry-allowed exchanges. I'm going to sort of back away from that very, very difficult question and just try to look at the simplest possible context. So what's the simplest consistent model we can write down? And then sort of throw these questions at it. Can one find a zigzag phase near this ferromagnetic KIDAV limit? And with these anisotropic interactions, can you understand why there might be these low energy spin excitations? So the simplest limit we can come up with is we remove all the monoclinic distortion, remove all the trigonal distortion, we remove all the further neighbor couplings. So we look at the nearest neighbor model alone without any distortions. As we mentioned in the previous talk, if you do this, the allowed terms are this JK gamma model, this Heisenberg KIDAV gamma model, where we have the Heisenberg coupling and the KIDAV coupling we saw before, but we also have this symmetric off-diagonal exchange. So the structure of this, so the KIDAV bonds, for example here,